Hey Class 12 champs, welcome back to the channel. Have you ever wondered why some chemical reactions, like the burning of a cracker, happen in a split second, while others, like the rusting of iron, take days, months, or even years? Well, that's exactly what we are going to uncover today. We are diving into one of the most practical and fascinating chapters in physical chemistry, Chemical Kinetics. The word kinetics comes from the Greek word kinesis, meaning movement. So, simply put, chemical kinetics is the branch of chemistry that deals with three main things. 1. The rate or the speed of a chemical reaction. 2. The factors that affect this rate. And 3. The mechanism by which the reaction occurs. Thermodynamics tells only about the feasibility of a reaction, whereas chemical kinetics tells about the rate of a reaction. For example, thermodynamic data indicate that diamond shall convert to graphite, but in reality, the conversion rate is so slow that the change is not perceptible at all. Therefore, most people think that diamond is forever. Just as the speed of a vehicle represents how much distance changes with time, the rate of a chemical reaction represents how much the concentration of a reactant or product changes per unit time. The rate can be expressed either as the decrease in concentration of a reactant or the increase in concentration of a product. Since the concentration of reactants decreases during a reaction, the rate of disappearance is written with a negative sign to keep the overall value positive. The average rate calculated over a time interval cannot describe how fast the reaction is occurring at a specific moment. So, to determine the rate at an exact time, the instantaneous rate is used, which is obtained when the time interval becomes extremely small, that is, dt tends to 0. If all reactants and products have equal stoichiometric coefficients, the rate of disappearance of reactants is equal to the rate of formation of products. But when the coefficients differ, the rate is divided by the stoichiometric coefficients to maintain consistency. For gaseous reactions carried out at constant temperature, concentration is directly proportional to partial pressure, and therefore the rate of reaction can also be expressed in terms of the change in partial pressure of the reactants or products with time. The speed of a chemical reaction depends on several conditions, such as how much reactant is present, the pressure for gases, temperature, and whether a catalyst is added. To understand how the rate changes with concentration, scientists use something called a rate law or rate expression, which is a mathematical way of showing how the concentration of reactants affects the reaction speed. Experiments show that as a reaction continues, the reactants are gradually used up, so their concentration decreases, and therefore the reaction becomes slower. However, if the concentration of reactants is increased at the beginning, the reaction happens faster. The rate law includes a constant called rate constant, which depends on the reaction and temperature. From the rate law, we get the order of reaction, which tells us how strongly the rate depends on the concentration of each reactant. The order can be 0, 1, 2, or even fractional or negative, depending on experimental results. A zero-order reaction means that the rate does not depend on concentration at all. It is important to understand that the order of a reaction cannot be predicted by simply looking at the balanced chemical equation. It must be determined through experiments. Another helpful idea is molecularity, which tells us how many particles, that is atoms, ions, or molecules, must collide at the same time for an elementary, that is a single-step reaction to happen. If one particle reacts, the reaction is unimolecular. If two particles collide together, it is bimolecular. And if three particles collide together, it is termed as termolecular. Reactions involving more than three particles at the same time are almost impossible in one step. Molecularity is always a whole number and only applies to single-step reactions. Most real reactions do not happen in one step. Instead, they occur through a series of smaller reactions called reaction mechanism. In such cases, one step is usually much slower than the others, and this step controls the overall reaction speed. This slow step is called the rate determining step. Just like the slowest runner in a relay race decides the final time, for reactions with multiple steps, the order of reaction comes from this slow step, not from the overall equation. The relationship between concentration and rate reaction can first be written as a differential rate equation. But measuring the instantaneous rate from a graph is often inconvenient because it requires finding the slope of a tangent line at a specific point. To make calculations easier, this differential rate equation is integrated to form the integrated rate equation, which connects measurable quantities such as concentration at different times and the rate constant. The integrated rate laws are different for different reaction orders, so we study them separately. A zero-order reaction is one where the reaction rate does not depend on the concentration of the reactant. When the rate law for such a reaction is integrated, we get this equation. This equation shows that concentration decreases linearly with time. So, when we plot concentration versus time, we get a straight line with a slope of minus k and an intercept equal to the initial concentration. Zero-order reactions are uncommon and usually occur when a catalyst surface becomes saturated, meaning increasing the reactant concentration no longer changes the reaction speed. Examples include the decomposition of ammonia on hot platinum and the decomposition of Hi on gold surface. A first-order reaction is one in which the reaction rate depends directly on the concentration of one reactant. When the rate law is integrated, we get this equation. Many chemical and radioactive processes follow first-order kinetics. Another important concept is the half-life, the time needed for the concentration of a reactant to become half of its original value. In zero-order reactions, half-life depends on the initial concentration. But for first-order reactions, half-life is constant and independent of concentration. This makes first-order reactions easier to study and predict. Sometimes, a reaction appears to be first-order, although more than one reactant is involved. This happens when one reactant is present in large excess, so its concentration remains nearly constant throughout the reaction. Such reactions are called pseudo-first-order reactions. Examples include the acid-catalyzed hydrolysis of ethyl acetate and the inversion of cane sugar. Increasing temperature generally speeds up chemical reactions. For example, nitrogen pentaoxide decomposes much faster at 50 degrees Celsius compared to 25 degrees Celsius or 0 degrees Celsius. And potassium permanganate reacts faster with oxalic acid when heated. Experiments show that for many reactions, a rise in 10 degrees Celsius almost doubles the rate constant. This temperature effect is explained by the Arrhenius equation K equals to AE to the power minus EA upon RT, where K is the rate constant, A is the frequency factor, EA is the activation energy, R is the gas constant, and T is temperature in Kelvin. According to Arrhenius, reactant molecules must first form an unstable activated complex before converting into products. And the minimum energy required to form this complex is the activation energy. From the Maxwell-Boltzmann energy distribution, we know that not all reacting molecules have the same kinetic energy. When temperature increases, more molecules gain energy equal to or greater than the activation energy, which increases the reaction rate. Taking the natural log of the Arrhenius equation gives a linear form where a plot of ln k against ln by t gives a straight line from which activation energy and the frequency factor can be calculated. Thus, higher temperature or lower activation energy increases reaction rate and the value of K. A catalyst also increases the rate of a reaction without undergoing permanent change. It works by providing an alternate pathway with lower activation energy. Since the barrier becomes smaller, more molecules can react and the reaction becomes faster. A catalyst does not change Gibbs free energy or the equilibrium constant of a reaction. It only helps the system reach equilibrium more quickly. If a substance slows down the reaction instead of speeding it up, it is called an inhibitor. While the Arrhenius equation helps in understanding how temperature affects the rate of reaction, collision theory provides a deeper explanation of how reactions actually occur at the molecular level. This theory was developed by Max Strauss and William Lewis, and it is based on the kinetic theory of gases. According to collision theory, molecules are treated as small hard spheres that must collide in order to react. The total number of collisions happening per second in a given volume is called collision frequency. However, just colliding is not enough for a reaction to occur. Only those collisions where molecules possess enough energy to overcome the activation energy barrier and collide in the correct orientation can successfully form products. These are known as effective collisions. For example, in the formation of methanol from bromoethane, the molecules must face each other in a specific direction. If the orientation is wrong, they simply bounce apart without reacting. To account for this requirement, collision theory introduces a factor called the steric factor, which represents the probability that colliding molecules are correctly aligned during a collision. Although the theory works fairly well for simple systems, it does not accurately predict reaction rates for complex molecules, because not all collisions are effective and the actual shapes and structures of molecules are more complicated than hard spheres. Overall, collision theory explains that both sufficient energy and proper orientation are essential for a successful reaction, making it an important concept in understanding how and why chemical reactions take place. Alright, that brings us to the end of today's revision on chemical kinetics. If this explanation was helpful, give the video a thumbs up, share it with your classmates, and hit the subscribe button and the bell icon.
Thanks for watching. Keep studying smart, and I'll see you in the next one. Bye for now from RJK.